Good day. In this video, we will talk about what happens when the particle is under constant acceleration. So we do have acceleration. That means the velocity is changing all the time, but that acceleration is constant. We're still in the x-axis, one dimension. So if I plot a velocity versus time plot, right? Velocity versus time, and I'm telling you the acceleration is constant, then this is what we're gonna get, a line, because remember that acceleration is, well, the slope of the velocity time graph. So if we have constant acceleration, we have a constant slope, right? The slope is your acceleration. What does that mean? What would that mean in terms of the acceleration versus time graph? This is what the last thing we did in class and in the last video. So we will know the acceleration, well, is constant. Well, even though that doesn't look constant because I'm very bad at drawing, but it will be a straight line. Okay, so that's it. And this also means that because the acceleration is the same all the time, then the average acceleration will be equal to the instantaneous, right? Just like we did with constant velocity model. So now in the constant velocity, in the constant acceleration model, well, this is true, which makes this possible instead of this was the average. So now this is going to be the instantaneous, right? We can express the instantaneous in terms of the delta instead of the derivative. And that gives us the following equation. Acceleration instantaneous is final velocity in x minus initial velocity in x over final time minus initial time. But if we make this 0, then, well, we only get final minus initial over the time. So this is one way to express this. Another way to write this equation is the same equation, just a different flavor, is that the final position in the x-axis, do this again, the final position in the x-axis is, the final velocity in the x-axis, excuse me, is going to be the initial velocity plus the acceleration times time. So these two equations are extremely powerful and very important for us, and I'm going to call this equation 1 in the constant acceleration package. Another graph we can generate is the position versus time based on these two. And if we do that, well, remember that the slope in the position time graph is the velocity, but the velocity is increasing. That means the slope also needs to increase, and then we will have something that is curved like that, with two different slopes, well, with many different slopes, right? A slope here, a slope here, a slope here. You see, the slope increase because the slope is the velocity. Well, this makes sense, right? Also, remember what I told you. The acceleration is the second derivative of position with respect to time, and we call this second derivative the curvature. Curvature as in happy face, sad face. So if the acceleration is positive, the curvature is positive. If the acceleration is negative, the curvature is negative. And look, this acceleration is positive, it's above this 0. So that means the acceleration will give us a positive happy face curvature in our position graph. You see, this is a happy face. Well, half a happy face at least. see positive curvature. So every time you have acceleration, the slope, well, constant acceleration, the velocity will change linearly, and the position changes with a little curve, happy or sad, depending on the sign of the acceleration. So these are the three plots, and for constant acceleration. Now look, from this graph, from the velocity versus time graph, we can see that because this is linear, the velocity is changing, of course, but we could calculate the average velocity by just doing, the average, taking the mean, meaning like if we start here with an initial velocity, and this is our final velocity at this point, well, the mean velocity will be just velocity initial plus velocity final over 2. That's another equation, equation 2. We can generate more equations. You remember this, the definition of average velocity was delta x over delta t. So I'm going to plug equation 2 here, and that's going to give us velocity initial plus velocity final over 2, which is the average velocity, so it's this part, and then this must be equal to delta x over delta t, right? So if I solve, which means final position minus initial position over delta t. So solving for the final position gives us this initial position and then plus 1/2 of velocity initial, velocity final times time. Remember that time initial, we're going to say is 0. And that's another equation. That's equation 3. This just comes from remembering that the average velocity is also this, now that we found this other way to find the average velocity. All these equations I'm writing right now are just for constant acceleration, the constant acceleration scenario. So we have 3 equations already, and we're going to generate another one, not 2 more. To generate the next equation, I'm going to use the velocity time graph that we had before, right, with initial velocity and then final velocity here, right? So for that, I must ask you to remember what we said in the in class. Actually, let's remember it together here. When you have constant velocity, okay, constant, like here, right? Remember that the average velocity in x is delta x over delta t. So delta x is average velocity times delta t, which is, well, for constant velocity, this is also the average. This is delta t down here. So, well, when you multiply height times base, the area is your delta x. Well, the same thing happens here. This area is also delta x. So how do we find the area? Well, I'm going to divide this area of a trapezoid into a rectangle and a triangle. We know this is delta t, so my displacement is base times height. So the height is the initial velocity times the height, which is, times the base, which is delta t, plus the area of the triangle, which is velocity final minus velocity initial in x, right? That's this part here, final minus initial, times the base, which is the time, And because this is a triangle, I have to do here 1/2 of that. Now remember that by definition, the average acceleration, which in this case is equal to the instantaneous acceleration, is velocity final minus velocity initial over time. Well, that means from this equation, velocity final minus velocity initial is acceleration times time. So I'm going to replace this here, and this is going to give us the following equation. Instead of Vx minus v final minus v initial, I write acceleration times time times delta t, but we had another delta t, so I'm going to write the squared, and that's our equation 4. The last equation comes from combining equation 1 with equation 3. And I'm going to let you show for yourselves that when combining equation 1 and 3 with a little bit of algebra, you can arrive to the following equation. V squared final minus V initial final is equal to 2 times the acceleration times the displacement, right? And that will be our equation 5. Okay. So now we have 5 equations at our disposal. They are all on your equation sheet. And if they're not there, please just add whatever you might require for tests and quizzes. All of these equations are the kinematic equation. Kinematic equations. And they work. Remember, they're telling you how things move. We're going to use them for that reason. How things move if acceleration is constant. You cannot use any of these equations when the acceleration is not constant. Which equation you should use, well, depends on what information you have at your disposal at the beginning of the problem. Let's try an example. So we have this problem. A jet lands on an aircraft carrier at this speed. We write it down. Initial velocity in x is 63 meters per second. They're saying that what is the acceleration? So we don't know. If it stops in 2 seconds. So we're going to assume initial time is 0, final time is 2 seconds, because there's an arresting cable. And then if the jet touches down at position initial equal to 0, what is the final position, right? So we have 2 unknowns. I did this little drawing. So the jet comes and is going to land here at the initial position when time initial is 0, and it's going to stop at a final position when final time is 2 seconds. So because we want acceleration, we look at all the 5 equations I gave you before, and I'm going to select this one, the definition of acceleration, because it's constant, right, assumed constant. Then I can simply write change in velocity over change in time, which is final velocity 0, initial velocity 63, final time 2, initial velocity 2, initial time 0, sorry. So this gives you 31.5 negative meters per square second. To find the final position, I'm going to use this equation. So if I plug the numbers, initial position 0, initial velocity 63, time is 2, the interval, 1/2 the acceleration, negative 31.5, and the time is 2 squared. And when you do this, you get 63 meters. So these are our 2 answers. We'll do more problems in class.